for the students who are here. So this session is being recorded. And I'm just going to go to the first slide. And so this has some remarks by me and things like that. And I think, Linda, I'm going to be able to share on top of this, and we can get back to this somehow. I think you know how to do that, so that's good. So I'm going to wade in, make a few remarks, as I often do. And then I'm going to give the floor to Linda, and she can make some remarks if she's choosing to. And then we'll have an opportunity for student Q&A. Now, often what we do is your questions are always welcome, and so you can ask them before, but there's at least a time when we pause and say, well, let's hear from the students. So anyway, that's kind of what will happen as our opening volley. And then we'll do some content, and tonight's content is going to focus on Doppler shifts, the physics of the Doppler shifts, the physics of beat frequencies, and this has huge application to Doppler ultrasound. And I haven't written your final exam yet, but I'd be really surprised if when we come up with a study guide, I don't say, oh yes, and there is a Doppler ultrasound problem that's here. So this is important not only for your craft, but for the tests that you'll be taking here as well. And a lot of the work that you would do, I think, will end up being Doppler kind of studies. Okay, now after tonight, there are exactly 4 meetings of this class. And maybe I should say that there are 5 meetings of this class, but the 5th meeting is going to be the final exam, which will happen on 12/13. And so, we'll have 4 regular meetings of this class, and then we will have the final exam administration that will happen. And I want to emphasize that this is the last time that we will meet this week, although this will not be the last time I will be doing math this week. And I imagine I will be doing math, thankfully, on Thanksgiving, and I'll be doing math, other times. So I could be sending you something to look at. I've already recently sent you some additional videos to watch, both for the NET class and for the VCM class. But anyway, so after tonight, there are 4 regular meetings, and there is no class on Wednesday. And so, and Linda may update you about the GSG schedule whenever we get to that thing before. There is good news to report. We're on track to finish the material that we're to finish comfortably in those 4 sessions. It's not going to be a huge rush, so that's going to be good. And in fact, there should be some time left, not a lot of time, but some time left for some VCM review within the VCM context, and we share those videos with everybody. So that's really a review for everybody. There will be a study guide provided, but the study guide is going to be my kind of study guide, where I will say, what types of problems I will be asking. So for example, one of these type problems, I'm sure will be a Doppler problem. And so, that's why it's important for you to stay tuned tonight. And I will also share the grace notes beforehand, so you have them, but the grace notes are pretty much always going to be whatever is at the end of the chapter in the physics groups, and those will be made, I guess, be made available. I don't know why I typed it like that, but those will be made available. Again, any accommodations should be established as soon as possible, because I'm trying this accommodations drill with the testing center folks again, and hopefully I've cracked the code on that. So send me emails, and if you're sending me emails about that, tell me the accommodations, that the accommodations are in the subject line of the email. That's basically the title of the email is accommodations. And last but not least in my narrative here, I want to give you an update on the book saga. and workarounds. Now, as you know, I spent an enormous amount of time early in the term lining up those books because there were a number of people that wanted the books. I never said the book was required, but the book, did have selected chapters from the statistics and from the physics. And so I shared that with you. I established the protocol for accessing it, and I shared that with you. And many students who wanted to buy the book ended up getting it that way. So I did share with you some correct kinds of things. Now, recently, there have been some students who have wanted to get this book, but they said they weren't able to do it and because I don't know, whatever I had established previously that worked, they were saying wasn't working. So I did contact Pearson yet again to check if maybe, and this was my guess, they'd established an enrollment period for students, and they pretty much said they didn't. But I'm going to share with you the response that I got today, and then we'll talk a little bit about that and maybe some workarounds. So Linda, I'm going to, and I think you're letting me share my screen. So I'm going to share my screen with you, and I'm going to show you. And Linda, I think I copied you on this, but I don't know if you've had an opportunity to read it. So anyway, I'm sharing my application screen, and I'm going to share the email that I got from Pearson about this. So I'm sharing my screen, and now what I'm going to do is I'm going to go to a new window in Google, or Chrome, I guess is what I want to say. I'm going to call up my email. And I have to log in. Okay, and we will be here, and I have to have them call me on the cell phone or something so I can log in. Okay, so they've called me, and now I'm logging in, and I'm looking for not McGraw-Hill, but this is from Pearson. This is a contact that I have at Pearson, Carly Olden, who is really a master at this kind of stuff. Okay, so here said, please provide this link to students who want to complete a purchase of the e-text. Now this is actually, I should make this smaller, hold on so you can see it better. This is actually what I shared with you before. But anyway, this students will be asked to sign in or create an account if they've not already signed into the platform. Once this is done, the student will be able to complete the purchase. And Carly says that she tried this process using her own student demo account, and it worked without issue. And let's see, I think she says I was in Google Chrome. So you might want to make sure you're trying that. And then she showed you some screenshots. So you're down here, and there's a place where you can get online access. Now, if you purchased an access code from the testing, not the testing center, but from the bookstore, you can click redeem, and it'll ask you to type this in. Or if you want to buy it, you can go over here. Now, I told you earlier that if you bought it from the bookstore, you paid more than this. But still, if you've already bought it, then you've got it, so you can do it this way. Now, when I sent the note back to Carly, I told her that, let me go and find this somewhere. This would be in the sent category. So this is the note that I sent back to Carly. I said, this does look identical to what I shared with you guys earlier, but perhaps there's some subtle difference there that will work for some of you, or maybe some of you didn't try Chrome. But then I say, well, perhaps they will be able to use it now. So, I am sharing this with you, not only here, but I'm going to work with Linda to post this on actually, I will do it, Linda, you don't have to, but I will post this email from Carly there, not as an email, but I will post it as a Word document, but you can read the whole thing, and that will be good. But I also say that I will follow up with them. Those are the students who have struggled with this, to ensure that they can make it work this time. So anyway, I've invested some more time in trying to give another opportunity here, and I'm asking that anyone who is struggling with this, still struggling with this process after you perhaps try this one more time, please come to my office hours. And I do have a workaround that I've done in the past for students who were unable to get this to work, but I'm hopeful that people will be able to get this to work this time. So I'm logging out of my email for right now. And Linda, can you throw the PowerPoint slides back up again?
Of course, just give me 1 second.
And there's probably a way for me to do that, but I wasn't really sure how to do that, so.
That's all right.
Okay, so that is my book saga in workarounds. And I think I've talked about all this stuff, so I'm pretty much finished with what I was planning on saying tonight. Linda, do you have anything to report or that you'd like to add, or whatever you want to say?
Not too much to report. We will not have a GSG on Wednesday due to the break. So hopefully you guys will enjoy some time off and we can hit the ground running again on Monday, okay?
All right, and did you have some traffic today?
We did have 2 people show up, not at the same time, but as you guys know, GSG is kind of a come whenever you want, leave whenever you want sort of deal. So even if you can't make it right at 5, then feel free to stop by at any time, okay?
And I did have students over the weekend when I was in the Learning Commons doing just some of my a weekend hanging out, and there were some 1120 students came in, and I think we moved the ball, so that was good. So Linda, I'm assuming that there's nothing else, I guess, so that it can be fine. And let's go to student Q&A, and I'll count to 10 Mississippi to give people a chance to organize their thoughts if they want to offer something. Okay, your questions, as always, are always welcome, and so you can ask them whenever they come to mind when we're going through things. And we're going to then wade into the whole idea of Doppler shifts and beat frequencies, and eventually talk about Doppler ultrasound. And I am prepared to even go further than that if we need to or can. Okay, so I'm going to advance the slide then. And we're going to talk first about beat frequencies. Now, the reason I'm talking about beat frequencies first is that it turns out the beat frequencies have a lot to do with the Doppler effect. So I'm talking about this first. And in fact, this I think happens in your book before that as well. So I'm just going to read this. And this is stuff that I'm really pulling from the lecture that I already recorded, but I think it's worth going over again. Okay, so the idea is that you have 2 sound waves with slightly different frequencies. So I'm pointing up here, and I think Linda told me you can see me wiggling my cursor. Is that true, Linda?
So we can see your cursor if you're sharing your screen, but since we're just sharing a PowerPoint right now, then we can't see it.
Okay, so maybe I will grab a pencil and make the pencil some certain color. Maybe I'll make it red today, and then you'll know where I am. Okay, so the idea is we're up here, and now you can see where I am anyway. And so we have two sound waves with slightly different frequencies. And what really happens is in a Doppler ultrasound environment, what you have is you have the transducer frequency that you're sending off, but then the frequency bounces off something that it hits, a bone or an organ or something, and it bounces back. So that certainly happens. But when the sound wave is reflected, if the object is stationary, it just reflects exactly the same frequency. But what we're going to see is if the blood cell is moving, it doesn't reflect back exactly the same frequency. It reflects back something that is a slightly different frequency. So this phenomenon is happening. Okay, now so these waves have slightly different frequencies, but they move as time goes on. And what you can see is that this, and you could think about this, what one wave as being, oh, I will call that, it's sort of a shade of red, and the other one is a shade of blue. And so they're interacting with each other. And sometimes they interact in a destructive way. That means they're reducing the volume. But other times, what they're doing is they're adding together. And that's what's actually being talked about down here. So when two waves with differing frequencies interfere, the resultant wave fluctuates in amplitude. Sometimes they interfere constructively when they are in step, and they interfere destructively when they are out of step. So the resultant wave waxes and wanes. Now, waxes means gets bigger, and wanes means gets smaller in intensity, and that forms beats. So you see, when these waves are encountering each other, what you get is a beat wave. So this is the beat wave that you see here. And here's another beat wave that you see here. And there, in fact, underneath this, they call this a beat. Okay, so that's what's happening here. And so you see, when the blood cells are moving either away from you or towards you, they form a beat frequency. And you should realize that the beat frequency, and this is, I'll talk about the proof a little bit, but the only thing that is in your equations is that the beat frequency is F1 minus F2. Now I will prove that it is F1 minus F2 later, but I don't expect you to know the proof, but I do expect you to be able to use this equation. And in fact, later on, when we're talking about ultrasound, Doppler shifts in ultrasound analysis, what's going to happen is this, in fact, is the Doppler shift, is this thing that we're talking about right here. Okay. So that's a little bit of a discussion. And here is, and this is in your book, it's in my video. You really don't have to do this, but it is a nice little proof, because what they tell you is that if these two things are really close together, then what happens is, I think I have to get my pencil again. So now I think I have my pencil again. And so what they tell you is that the period, which is time, of the beat is one of the signals is goes through n cycles, but the other goes through n minus 1 cycles, and that means that the period of the beat is this, and it's also equal to this. Now what you can do is do some math, and Linda and I would do this math for you if you wanted, but I think I'm just going to tell you, if you do math, what you can do is eliminate the n from this equation. You can find that the period of the beat is this, and since the period is inversely proportional to the frequency, you can turn it upside down. And so whenever you have this, then I have T2 minus T1 all over T1 times T2. I divide that denominator into each term. And so when I take T2 over T1 over T2, I get 1 over T1 minus, and this is 1 over T2. And up here we assumed that the period of T1 was less than the period of T2. So that means that this is in fact greater than 0. But this 1 over T1 minus 1 over T2 really is F1 minus F2. So this is the equation that you certainly want to remember as we go forward. So I think what we should do now is do some problems. And Linda, what I'm going to ask you to do is please stand ready to do some calculation if we need some calculation with a calculator. Okay?
You got it.
All right. Thank you, Linda. Okay, so what we have here then is I'm reading problem number 45 just to get us used to this. And we may do all 4 of these problems, or we may just do a couple. I'll kind of keep track of time and see how we're doing. You certainly could go back and do all of them, and that would be fine. And some of the students who've been coming into the Learning Commons have been, in fact, working extra problems, and they've been looking at the solution manuals that we have in the Learning Commons, and it's been a good thing for them. And then if they have questions beyond that, they've been asking me questions. And I think those students and I are moving the ball. I think that's good. And I'm sure you guys are moving the ball when you're attending Linda's sessions as well. Okay, so here we go. A trumpet player is tuning his instrument by playing a note simultaneously with the first chair trumpeter who has perfect pitch. You don't really have to know that the trumpeter has perfect pitch, but the trumpeter will be blowing exactly the note that they're supposed to. And any of you who have been in orchestras know, perhaps you know, in fact, if you're in an orchestra, I'm pretty sure that you know that the note that they play to tune to is an A, and an A is 440 hertz. Okay. But the first chair's player note was exactly 440 hertz. But as people listened to the trumpet player and this first chair player playing at the same time, they hear 2.8 beats per second are heard. So the question is, what are the possible frequencies of the other player's note? Now that means the other player's note is off a little bit because they're hearing beats, and they would not hear any beats if the frequencies were the same. Okay, so what are the 2 possible frequencies of the other person's notes? Well, you see, they heard 2.8 beats per second, so that means one of these is higher than the other. So what I'm going to do is I'm going to share my screen, and I'm going to share the whiteboard. All right, so we know that the beat equation is F1 minus F2, and that is the beat frequency, and that's the frequency of the beat. Okay, but what we heard, or what we were told, is that the the difference between these two was 2.8, and that was, and again, these are differences in frequencies. So this is 2.8 hertz. because that's the beat frequency. So it comes in hertz. Now, one of these guys was the trumpeter, but we don't really know which one it is. So anyway, the possible for the, I'm going to list this be the first chair trumpeter, okay? But I don't know if it went this way or the other way. I don't know if this guy was 2.8 higher or 2.8 lower. And so this F2 frequency, there are two of these. And so this would be 440. And this is hertz, which is the frequency of A above middle C. And so this is 440 hertz, and then this is going to be plus or minus 2.8 hertz because you don't know which way it is, above or below. And so we get that, and Linda can calculate this, but actually I'm not even going to make her do this. So this is either 442.8 hertz. Maybe I should write this down. So this is either 442.8 hertz, the other trumpeter, or it could have been the minus, which would be 437.2 hertz. Questions on this problem? I'll count to 5, Mississippi, in case there's questions. But this is trying to get you at what is a beat. I heard some sort of open mic, but I didn't hear a question, so that might have been no one asking a question, or maybe Linda was
That
going
was
to come.
me, Monica. Sorry. Can you
Well,
explain
don't be
again
sorry.
why?
Do you have a question? Go ahead.
Yeah, explain again why we would do both plus and minus.
Well, okay. Here's what you did. When I say you did, here's what the problem said happened. There were 2.8 beats that were heard. So maybe the conductor of this orchestra heard 2.8 beats. That means that somebody was off tune. And in fact, we're saying it's not the first trumpeter because we say that he or she had perfect pitch. So she isn't wrong. But that means that the frequency of the other trumpet was off by 2.8 hertz. But it could have been 2.8 hertz higher in frequency, or it could have been 2.8 lower in frequency. So F2, and I guess if I was really trying to do this mathematically, maybe there's a benefit in this, I would have put absolute value there. Okay, but then what happens is this F2 is either 2.8 above the right frequency, or it could be 2.8 below the correct frequency. And that's how we got to this one. Are we okay with this, or and Linda, if you want to jump in and improve on any explanations, feel free. Monica, did that help?
Yes, it did. Thank you.
All right. I'm going to count to 5 again, a little faster this time, but I always restart my count when somebody asks a question because it might stimulate other questions. Okay, I hit 5, Mississippi. And Linda, I'm going to try that fancy thing you taught me how to do about erasing this all at once. And now that is gone. So now, Linda, let's go back to the slideshow and look at another problem, please. And Linda, on this one, I don't know, but on this one, you might end up using a calculator. Do I need to quit sharing?
Nope, I'm just bringing it back up.
Okay, so she's throwing that on top of us. And we're going to read another problem. Okay, number 46, 2 tuning forks. And I showed you kind of, I drew a picture of what a tuning fork is, but if you strike a tuning fork, it starts vibrating really fast, but it makes a noise too, so you can hear it. And again, if we were blessed and we're in class together, I could strike a tuning fork and hold it near your ear. You'd hear this. But we aren't in class, so you have to kind of use your imagination. But two tuning forks are producing sounds, but these are not identical sounds. One of the tuning forks is producing a sound that has a wavelength of 30.40 centimeters. And the other tuning fork is producing a wavelength of 30.96 centimeters. Okay, now these things are not in sync because the wavelengths are different. And so the question that's being asked here is, how many beats do you hear each second? And that's basically what is the beat frequency. Okay. All right. So now what we're going to do is we're going to do this, and I'm going to try to memorize these numbers. And so you have one fork that's going at with a wavelength of 30.40, and these are all centimeters. The other one is 33.94. Now I don't know if you, and when I'm really talking about you, could hear the difference. It really depends on how great of an ear you have, because these aren't too different, but they're a little bit different. So I'm going to share my whiteboard with you yet again, and we're going to talk through this, okay? And Linda, there likely will be some calculation as we go through, so stand ready, if you will. Okay, so this is a drawing. I'm going over here. I will try black this time. So we know that the beat frequency, which is what we want to find, B-E-A-T, and that was a horrible thing, but this is the beat frequency. I guess I will erase that and make that a little bit better. Okay, so I'm going to type beat underneath this and see how that goes. So this is the beat frequency. So this is B-E-A-T. The beat frequency, but now we know the beat frequency is equal to the difference in the frequencies. Okay, so that is the beat frequency, and we want to find out what that is. But we don't have F1 and we don't have F2, but actually we have something almost as good. In fact, we have something that's every bit as good, because F1 is V over lambda 1. And you remember, I think it was 2 lectures ago, but we spent a lot of time talking about frequency is equal to the velocity of the wave over the wavelength. So that says this first thing has a wavelength, and this is V over the velocity. And V here is the speed of the wave, and that's the speed of sound. And we're going to assume, and I think it was Monica asked the question, where did this 344 come from? And I remember answering that question saying, Monica, that's the speed of sound in air, is 344 meters per second. And you see, we're doing this in air. So what happens is the velocity of sound really is going to be the same. It's going to be 344 no matter what. So this is going to be lambda 2. Okay, now I can factor that V out of here. So this is V times, this is 1 over lambda 1 minus 1 over lambda 2. Okay, and then what we're going to do is write these numbers down. So this is going to be equal to, now the velocity of sound, and not in soft tissue, but in the air, which is where tuning forks are, is 344, and this is meters per second. But then this is times, and the smallest number here is 0.344 meters. And again, I got to use meters. I know it told me centimeters, but I have to use meters because the units have to work out. And so what I'm going to do is this is going to be 1 over, and I'm using the smaller number here, otherwise I could use the absolute value. But the smaller number is 0.3394. That is meters minus 339. I did not write the 4. 94 meters. Linda, use the 4 whenever you were doing the calculation, please. And the other one is going to be 1 over, and this is going to be 0.3440. This is also meters. And as Linda will tell you, if the denominator is smaller, the fraction is bigger here. Now, when I multiply these things together, the meters will cancel, so I'll get reciprocal seconds, and 1 over seconds is hertz. So anyway, I'm going to ask Linda to, and Linda, just pound this into your calculator, and we'll get a beat frequency.
I'm getting 0.01355.
Okay. So when you do, okay, so, and did you, let's see. So did you multiply by the 344 already too? You did the whole thing?
Well, you said that was 0.344 on the outside, right?
This one is 0.3440, and this is point. So let's do one of these at a time. So I'm distributing it now. So Linda, what do you get if you divide 344 by 0.3394? And by the way, Monica
That
just
would
told us
be
she
1.01355.
Okay, so I think it is going to be 14 hertz, right? And that is 1 over seconds. Because see, we're taking 300 and we're dividing it by roughly 3. So we get, and you might have been giving me some scientific notation there. In fact, did you have that in scientific notation?
No, I thought you said that 344 meters per second on the outside was a 0.344 meters.
Oh, no, I am sorry. In fact, what I was saying, Linda, was this one over here.
Okay, gotcha.
And you see it's the same damn number, the same damn digits?
Yeah.
Yeah, so I was miscommunicating. But on the outside, it is 344.
Okay,
Now
then
we've
yeah, you get
explained it.
about 1014.
Yes, excellent. And then when you subtract off the other guy, you're going to get about, in fact, wow, I can do that in my head, can't I? That's 1,000 because the numbers are the same. Okay, so the answer is 14 hertz. And thank you, Linda, and sorry for miscommunicating there. Both of these are hertz, and your answer is hertz. And I think Monica got that answer too. Okay, so I'm going to pause for a count of 10 Mississippi just to see if anybody, I don't know, wants to talk about this more. Okay, well, I didn't get any additional responses, so I'm going to use Linda's technique to clear these annotations. I'm actually getting better, Linda, slowly. but I am getting better at this. Okay, so that is good. And I'm going to ask Glenda to show us the slides again, and maybe we'll do one more problem with beats just to do this. And 47 is an interesting problem, and you do have to do the absolute value, and you actually get some different solutions. But I think I'd rather talk about 48, which is a little bit of a concept problem. So I'm going to read 48, and we'll talk about it just briefly, and we'll go from there. This is called tuning a violin. And by the way, if you ever go to a symphony orchestra, this is what happens. The conductor will, in fact, shake hands with the first violin player. And actually, one of my students in differential equations is a first violin player. And he had a concert one night when we were having class, and he says, "Gee, I have this concert, and I'm really kind of an important person at the concert." And I said, "Well, you can. I mean, I try to be flexible, particularly with this student. He was a high school student." And I said, "Okay, I understand that. You said you're important. What instrument do you play?" And he says, "I play violin." And I said, "Are you the first violin?" And he says, "Yes, I am." And you see, I realized how important that is to a symphony orchestra because, in fact, the whole orchestra is seated, and then the first violinist walks in by themselves, and everybody claps for them. And then they go in and they play a perfect 440 hertz. They play A, and everybody tunes to the A. And after that, the conductor walks in, but then the conductor shakes hands with the first violinist because they're partners. They're the two main people. And then the conductor, he or she, gets up there and starts conducting. Anyway, okay, so a violinist is tuning her instrument to concert A, which is this 440 hertz. And she plays the note while listening to an electronically generated tone of exactly that frequency, and here's a beat of 3 hertz. So you see, she hears a hertz. Does it say she? Yes, it does. Okay. So this is a woman violinist, but she hears a beat frequency. Now, this electronically generated tone is right. So that means she is out of tune. So she has to fix this somehow. So here's what she does. She tightens her violin strings slightly and then measures again. And now she hears a beat frequency of 4 hertz. So the question is, what was the frequency her violin was playing when she heard the 3 hertz beat? And the answer is her violin was playing 443. Now you might say, well, wait, Jim, how do you know that it was 443 instead of 437? Because she heard that. Well, what I learned was when she tightened the strings, what happens is it got worse. It went up to 4 hertz. So that means what she wants to do is she wants to loosen her strings to go down 3, because when she tightened, she went up, and so she has to loosen her strings to get to remove the beat of 3 hertz, which means she had to be above the 440 hertz. So hopefully that made sense. I didn't write anything down, but I guess I will just count to 5 Mississippi to see if anybody wants to weigh in on this. And again, it's possible some of you may be violin players and may know all about this more so than I actually do. I do not play the violin. Okay, so I guess we're okay with that. And people are joining and leaving the session, so I know they probably have things going on. Okay, so that is good. So now what we're going to do is we're going to move on and stop talking about beats. I'm going to start talking about the Doppler effect. Okay, now, and a lot of times, in fact, I will tell you something that happens some evenings when I am lying in bed in my bedroom. And my bed is, I sometimes lecture from my bedroom, and I am lecturing from my bedroom now. I am not lying in bed, but I am lecturing from my bedroom. And my bed is about 8 feet across the room from me right now. I have a little desk station set up here. But sometimes I am in bed at night, and I will hear a emergency vehicle on the road. And this could be a police car sometimes, it could be a fire truck, it could be an ambulance, but I will hear this siren. And I live close enough to a major road that I can hear the siren. And I will hear the siren, and it will be coming to me at a low pitch for a while when it is farther away from me. And usually, just given the geography of my house, usually it is coming from east of my house, and so it will be coming this way, and so the frequency is low, but I'll hear it, and then the frequency will get louder and louder and louder as it gets closer to my house. And then I always hope that what will happen is after it gets pretty loud, I hope that it won't stay loud, because if it stays loud, that means it's stopping somewhere in my neighborhood, saying, oh my gosh, maybe something bad is happening to someone in my neighborhood. But many times, thankfully, what I hear is it gets louder and louder and louder. Then it gets softer and softer and softer when it goes past where my house is and goes further west in my story. Well, you see, that siren didn't change. What happened was that the siren was giving the same frequency the whole time. But what I heard was different, because the closer it got to me, the quicker the sound waves were getting to me. And that means the frequency was going up. Then when it went further away, on the other side, the frequency would be going down. And I could be, and I am stationary because I was just lying there in bed. Okay, now that's what the Doppler shift is about. And I'm sure you've all experienced that with your, um, with sirens and things like that. So anyway, here we go. The Doppler effect, and this was in the video, so this is nothing really new for those of you who watched the video. The Doppler effect is the frequency shift that occurs when a listener is in motion relative to a source of sound. The source and listener frequencies, Fs and Fl, and their velocities are related by an equation. Now this equation that I'm showing you is the master Doppler shift equation. And the reason this is a master Doppler shift equation is this has everything in it. It talks about the frequency that the listener hears. It talks about the frequency of the source. And it also talks about the velocity of the listener and the velocity of the source. And V is the velocity at which the wave goes. So you can kind of look at this little narrative here, which kind of shows you what's going on with the equation. So you have a policeman here on the left side. So I'm over here. This is the policeman, and the policeman is the listener. So he's walking along, and he's walking at a speed that is V sub L that way. Now you got this person over here who is the source of the noise. You can see the person is riding on a skateboard, so they're moving. And so in this one, the source is also moving with a velocity, and they're moving in the same direction. They don't have to be moving in the same direction. They could be moving in opposite directions, but these are moving in the same direction. But the wave, the sound waves, and then you can see this fellow has, I don't know if it's a guy or a girl, but anyway, we'll pretend it's a guy, is got a boombox on his shoulder and he's making music. And so what happens is, just like it did with those birds that we studied in the other problem, there are sound waves that are going out in spherical ripples. So these sound waves are going out like this, and the distance between each of these sound waves is going to be lambda, and this is V. So you see V equals, or let's do it the other way, F is equal to V over lambda, you know that, so there's frequency involved here. So the sound waves are going this way, and the sound waves are also going this other way, but what is happening is the source is moving. So you notice when the source is moving, it is scooching these two things together, and so the wavelength gets shorter rather than longer, and depending on these relative velocities, you have things that are happening. So you see, if you know the velocity that the wave is going, that's V, you know the velocity of the listener and the velocity of the source, and sometimes, like when I'm in bed, I'm not moving, but I'm also not the source, I'm the listener, so VL in my case would be 0. And so you see what would happen here is we would get, we could do calculations like this. Now, one important thing, and I think I can annotate this, I'm going to try to annotate this because I'm going to say that signs, S-I-G-N-S, really matter. Because sometimes things are minus a minus, some things are minus a plus, and it matters which direction you're going. Like, for example, it would be a whole different story if this policeman, I need to get my pencil again, if this policeman were walking this way instead of that way, then this would be negative compared to VS. So you've got to be careful as you're doing these problems, and I do a number of problems in the video that you watched. But we're going to do a problem here just to get our feet wet with this. And in fact, before we're done, we're going to go and we're going to talk about this in an ultrasound context. So Linda, I'm advancing the slides, and that's good. So now what we're going to do is we're going to, and what the heck, we're going to talk about number 49. Okay, so I'm going to read this, and then we're going to go, draw some pictures, and we'll talk about that, and so on and so forth. So here we go. A railroad train is traveling 25 meters per second in still air. Now that is how fast the train is traveling. So that 25 is an important number in our equation. The railroad train is also blowing its whistle, and its whistle is at 400 hertz. So that's the frequency, and this is the source. Okay, so let me do some things here. So, oops, that was a bad mistake. That didn't work out so well. And I really want to put that back. Maybe I'll try this. Okay, that covered that up, and I can't. Oh, I know what I can do. I can maybe just try not to do that. Try to turn that off. There we are. All right. So that's the source. I can't underline these things very well because my screen gets cluttered up with things. But okay, so that's what's happening. So the train is moving, but it's also sending a frequency note that is at 440 hertz, which is just a little bit below A above middle C. Okay. So then we ask, what is the wavelength of the sound waves? But the wavelengths are different. They're in front of the locomotive. You might be saying, oh, I see trains in this picture. This must be the same picture. This is not the same picture because you see you got two trains. Both of them are moving. Actually, this train's not moving, but this train is moving, but this train is blowing its whistle. This one's blowing its whistle, and you got a guy in the front, in the middle, that's doing something too. So that's a more complicated problem. That's what the picture is about. It's not about ours. But we say, what is the wavelength of the sound in front of the locomotive? What is the wavelength behind the locomotive? Now here we're talking about wavelengths, but then we say, what is the frequency of the sound heard by a stationary listener who is in front of the locomotive or behind the locomotive? Okay, so you got stationary listeners and so on and so forth. So we're just going to talk through this then, okay? And so A was in front of the locomotive and behind the locomotive. We're talking about the wavelength of the sound waves. Okay, so we're going to this, and this is number 49. Okay, so we will do part A, and I'm going to share my screen with you. And there'll be a blank chalkboard. I hope it is a blank chalkboard. Good, good. Okay, and so this is going to be now I'm taking the velocity of the source to be and I could take it to be positive or negative, but I'm defining my coordinate system this way. So I'm going to take this to be 25 meters per second. Now what that means is we're going 25 meters per second along the track, and we're letting this be a negative direction, okay? But then we're going to do lambda in this case because we're right in front of the locomotive. So lambda is equal to then, it's going to be velocity. Now this is the velocity of the source. So this is going to be the velocity of the source plus the velocity of the wave. Now we're doing this in air. So Monica, that's going to be that 344 again. But this is going to be a frequency in the bottom. And so what this is going to be, and Linda will probably do us the honor of doing a calculation here, but the velocity of the source is going to be minus 25 meters per second. But the velocity of sound is going to be in all directions 3, 4, 4. And there is no velocity of the listener because the listener was not moving. And so we're going to divide this by the frequency, which was 400 hertz. This is hertz, and hertz is reciprocal seconds, and this is meters per second also. So the answer to this is going to be the wavelength that we will have. Okay, so let's see. So Linda, what is the wavelength when we do this calculation? Please give me 3 significant digits, Linda.
3 significant digits would be 0.80.
Okay, and Linda, Linda, that was probably my bad saying that. This is what I want to have, which is, Linda did the calculation right, but this is hertz. And I'm just trying to match up with what my notes say. And
well, even if I give the exact answer, then I'm getting 0.7975.
Really? Okay. Oh, wait. I screwed that up. I wrote it wrong. Linda is right, pretty much as always. That's 9.8. I did a dyslexia thing there, Linda. I transposed the digits. So that's what we have. So thank you, Linda. Again, Linda is right. You can put that in your notes. In fact, Linda is almost always right. So that's what we have. Now I'm going to pause here and see if anybody's got any questions about what happened here. And notice that I pulled out this old equation that we had before. So I'm going to count to 5 Mississippi, and then we're going to say we're good with that. Okay, no one asked any questions, so that's good. And we could do other problems here too, but we'd be exercising this, these equations. So anyway, that's kind of the Doppler effect in these. Now it turns out that their Doppler effect, and I am watching my time very carefully, and so I'm going to skip ahead. And again, you should watch the video for more examples, and you could try some of these other examples that I have, and so on and so forth. But what I'm going to do is ask Linda to bring back the slideshow. We're going to move ahead, and we're going to talk about this in a ultrasound setting. And thank you, Linda. Okay, so I'm moving ahead. I know what slide I'm looking for, and I could never tell Linda what slide I'm looking for. By the way, here's some nice ultrasound problems here that maybe we'll talk about maybe next time, but not tonight. So this talks about Doppler ultrasound. I'm not going to read all this to you, but a Doppler ultrasound is an imaging test that uses sound waves to show blood moving through blood vessels. A regular ultrasound also uses sound waves, but you're creating images of structures inside the body, but it can't show the blood flow. So you see, a Doppler ultrasound is a different kind of ultrasound, but I'm supposed to be teaching you about that. And so what happens is it works by measuring sound waves that are reflected from moving objects. And when you think about moving objects, you say, oh, this is just like the Doppler effect that we did, and it's the red blood cells that are moving. So I'm going ahead then. I have a nice picture here eventually. And here is my nice picture. Okay, so this thing here, and Linda told me you couldn't see what I'm drawing, so I'll go over here so I can at least point. And maybe I will get a red pointer since we're dealing with blood. This speaker microphone that they're saying here this is actually a transducer. So what this transducer is you're sticking it on someone's body, and it is sending sound waves into their body. So the sound wave goes in, but it hits these blood cells, and it ricochets off the blood cells and comes back to, and they call this a microphone. So they're calling it a speaker microphone. It really is a transducer, but it sends the sound wave out, and the sound wave hits the moving blood cells, but then it comes back. But the difference between this and other things is it doesn't get the same frequency back. It gets a different frequency back because the Doppler effect is happening. Okay, so we'll read just a little bit here. So I'm saying ultrasound, and let's just suppose it has a frequency, in this case of, it could be a different number, but it's 2.5 megahertz. Now that's a big number. Is sent toward blood in an artery, and the artery is moving towards the source at 20 centimeters per second. So that's the little play that's going out here. So this is your transducer. You're blasting it into the blood vessel. It's hitting these moving blood cells, and it's ricocheting back. And your transducer is not only sending out the signals, but it's receiving the signals back. And it knows this is a Doppler study that you're doing. So what happens is we know, and the speed of sound is not 344 meters per second this time, Monica, because we're going through soft tissue, which has a different speed, which is 1540 meters per second. So we hit it, and what happens then? So we can say, what frequency does the blood receive? Well, the blood receives a frequency that was sent out. So it receives a 2.5 megahertz signal, but it's moving. So the question is, what signal does it return to the source? And we're going to talk about that because that is the Doppler effect. And then we ask, what is the beat frequency that's produced in returning the frequency? And this is another bigger picture of that same construct. Okay, so these are the kind of questions that we're going to be asking. So now we will go to the next thing, and notice that we're using the Doppler equations here. And so we say that the first two questions can be answered. The observed frequency is going to be the frequency of the source, which is the 2.5 megahertz. That's down here. Let me put it down here. So here is the 2.5 megahertz. And then this is the velocity of the wave. Now the velocity of the wave, though, is going to be the net of these two, because you see you got the speed of sound, but you also have the speed that the blood is moving at. And notice that the decimal points have been moved to make the units match. So you have to add those two together, and you divide those by 1540. Now I'm not going to make Linda do this, but if Linda were to multiply all this stuff together, she would get this number, because that is the frequency. So you see, because this blood is moving, the blood cells don't observe a frequency of 2.5 megahertz. They get 2.5 megahertz and a little bit more. That's so the frequency is jacked up a little bit, and in fact it's jacked up to 325. But now they're still moving, and they're sending this is the frequency that they're observing, but now that is the frequency, the velocity that's happening there. So now we want to say what happens when we go back to the transducer, and that's on the next slide. Okay, well, the transducer, you see, we're saying what frequency does the transducer observe? Well, what the transducer observe is, this is the equation that we will have. And let's see, I need to not do that, but that wasn't what I really wanted to do. I really wanted to go up here and grab this thing again and try to do this. So this is the frequency that it observes. But you see the sound wave is going in the opposite direction of the velocity of the blood. And so this ends up being 1540 minus the speed of the blood divided by the speed. So the point you should remember here is there are two Doppler shifts going on. And so if Linda were to calculate this one, this is what she would get. So you see, here's what we're observing. We sent out 2.5 megahertz, and we got back this. That means that the Doppler shift, or the beat frequency, was 649 hertz. And by the way, I know we've talked about this, but 649 hertz is in the band that you can hear, because you can hear from 20 hertz to 20,000 hertz. So you certainly can hear this. And if you were ever in a room and they turn up the volume on the speaker, you can actually hear a Doppler study, and it'll go kaplunk, kaplunk, kaplunk. You can actually hear the Doppler study, even though these other frequencies are too fast for you to hear. So that's kind of how it works in general. And so we go through and we find out the Doppler shift was this 649. And again, you can hear that. Okay. And I don't think we're going to talk about this, but I am going to show you one other slide. Okay. Because you might think, okay, this is pretty easy. It's not quite as easy, because Linda, can you make that picture bigger?
So I can't personally, but if people go in the top left corner, then there's actually a magnifying glass with a plus button inside of it. So they can zoom in.
Okay, so anyway, here's what I want to say. You aren't always exactly in line with the flow of blood. You're usually at an angle, and the angle is shown here to be theta. And if you look at this triangle magnified, you will see that the velocity that you're observing is really not the velocity of the blood, but it's the velocity of blood times cosine of theta. So that means that, and I'm going to call your attention to this one right here. And thank you, Linda. I wasn't sure what we could do and what we couldn't do. But this is a really important thing, because I will tell you, most students like this ultrasound equation better than they like the other one, and you certainly are free to use it. So what it says here is the Doppler equation, usually written in ultrasound books, is this way. And I guess I will try to write this, Linda, maybe because I can't make it bigger easily for people. So this says delta F, that's the Doppler shift, the change in frequency, is equal to 2. And the reason the 2 is there is because there are 2 Doppler shifts that happen. One happens when you hit the blood, and the other one happens when you hit the receiver again. So there's 2 Doppler shifts. So that is delta F is equal to 2. This V is the velocity of the blood. And then there's a cosine of theta, and that's the angle that you make. And that's that angle that you see right here, because you're not making a perfect angle with the blood. And Linda will tell you, if you were making a perfect angle with the blood, it would be the cosine of 0, and the cosine of 0 is 1, so it would be perfect. But this is times cosine of theta, and I wrote that red on top of red. That's not good. I don't know if I have time to fix that. Maybe I do. Hold on. I'll do the drawing again, but I'm going to stop being red. I'll do the drawing this time. Instead of red, I'll make it black. Okay, so there's a cosine of theta that's here. So this is 2 cosine 2v cosine of theta times, and this is the transducer frequency. Now I'm just going to call this F sub 0, but you all should remember that that's the transducer frequency that is here. And then I have to divide by the propagation of sound in ultrasound, and often this would be something like 1540 meters per second. Okay, so you see, if you observe a Doppler shift of something, you put that on the left-hand side. And then the other side, it's 2. V might be the speed of blood. Cosine theta is whatever angle I tell you it is. And then I also told you what the transducer is, and I divide this by the speed of sound in the medium that we're going through. Now that's what they read right here. And that's an important thing for you to take away. And Linda, maybe I'm going to ask you to comment, but is this, Linda, in your humble opinion, and Linda probably is humble, but she really doesn't need to be because she's a very capable person. Is this an easier equation for students to use usually?
Oh, absolutely. It's way easier.
Okay, so that's a good, I guess, lesson to take away. Okay, again, we're almost ready to dismiss you, but I do have office hours tonight. If anybody, wants to try that thing, getting the book again, they can try it. And I do have a backup plan that's kind of a wild and crazy backup plan, but I don't know it'll work. If you come to my office hours, I'll do the wild and crazy backup plan. And in case you say, oh, but I can't come to your office hours, but I can come to Linda's thing, I'll tell Linda the wild and crazy plan as well, so she'll be armed with it. And so nobody needs to say, oh, I can't answer this, and they don't have to, call the dean or something like that and say, oh, gee, I'm not getting any help. So it's all good, okay? So anyway, I'll be at my office hours tonight at 9, and maybe I'll see some of you there. And this is pretty much our lecture. We'll talk a little bit more about the Doppler shift next time that we meet after the Thanksgiving holiday, but then we'll move on to Snell's law and other things with boundary behavior. So we're getting close. Everybody finish strong. Good night, everyone. Take care. And I need to stop the recording. Thanks, Linda, as always.